Waves? They be pretty cool. Dang, why you think we learn about them in school?
The objective of this lab was to find the speed of sound at room temperature and air using the resonant frequency of tuning forks.
To complete this objective, we needed to use the equation of velocity equals frequency times wavelength. Frequency is the number of wavelengths per second, and wavelengths is the length of one wavelength in meters. Together, they have the units of meters per second, or velocity. To find the speed of sound in air, first we grabbed a graduated cylinder. Then, we filled it with water. We took a PVC pipe and put it in the water. The water created a closed node around the bottom of the PVC pipe and an open space above it, creating an antinode. Then we grabbed some tuning forks and run them and then put them above the PVC pipe, slowly lifting the PVC pipe. When we heard a louder sound, we knew that we could assume that was the first harmonic. We measured the distance between the top of the water and the top of the PVC pipe.
With this information, we could calculate the wavelength and the speed of sound at room temperature. The first tuning fork we used had a frequency of 255 Hz, tube displacement above water of 34 centimeters, or 0.34 meters. To calculate the wavelength, we used L equals 1/4 times the wavelength. Then we could calculate the velocity using V equals wavelength times frequency. The velocity at room temperature was 347.75 meters per second. The second tuning fork we used had a frequency of 366.1 Hz.
Tube displacement above water.
0.23 meters. The calculated wavelength was 0.92 meters. Then we calculated the velocity, and that turned out to be 336.8 meters per second.
The actual speed of sound in the room was 344 meters per second, so our percent of air came in at a nice negative 2.15%.